Let's start. So last week we started talking about basically we finished the subject of normal shock waves, and we started talking about oblique shock waves, but and it was cut off at the very end because of an internet outage. But anyway, we will continue that topic today, the topic of oblique shock waves. But there's an important concept. This is also in your book, but I would like to cover that as well. This is about, for example, in many supersonic flying aircraft, at the nose of the aircraft. Let's say this is the nose of the aircraft. The cockpit is somewhere here, and at the very nose of the aircraft, you see generally a tube sticking out. Okay, this is called the pitot static tube. Okay, and similar to ones we are using in laboratories. Okay, so now the thing is, when this is a supersonic flying aircraft, so this means that the free stream Mach number will be larger than 1. But because of the shock wave around the aircraft, and especially at the very tip of the pitot tube, so if you focus in or zoom into this region, basically what you're going to see is you have a pitot tube which measures two things basically. It measures total and static pressures. It has a hole at the tip, so here it measures the stagnation pressure. From the side holes, it measures the static pressure as any regular pitot tube. So the thing is, using these two measured values, we can, or the flight computer actually calculates m infinity, what is the flight Mach number. The thing is, when the aircraft is flying supersonically, there is a shock wave generally sitting, right in front of this pitot tube. Okay, so there's generally a detached bow shock wave. So in this case, what we are measuring and what we want to know is this, the flight Mach number of the aircraft. What we are measuring are these, P0 and P. So how can we actually find it would be nice to find a relation, equation for m infinity in terms of some atmospheric quantities plus in terms of these measured values of stagnation pressure and static pressure. So we will do a little exercise to basically to do that. Okay, to calculate, to obtain this expression, and we will, in order to obtain this, so this is basically a pitot tube in a supersonic stream application with a curved detached shock wave, or we call it also a standing shock wave in front of it at zero angle of attack. So the flow is coming with no angle of attack towards the pitot tube. And we will assume that the shock wave in the vicinity just in front of the pitot tube is a normal shock wave. So we will simplify this problem as if this is a pitot tube, as if we have like a normal shock wave right in front of it. Well, this assumption is mostly true because in the vicinity of this inlet, we indeed, the shock wave angle is indeed close to 90 degrees. Okay, so this is not, this is kind of a reasonable assumption. So basically, it will approach with m infinity. So we will assume, first of all, steady flow and one-dimensional flow, steady one-dimensional. It's a shock wave problem, so we assume this is an adiabatic flow, okay? And we just assume that this curved shock, we approximated it as a normal shock wave in front of the pitot tube. And we would like to use certain relations. So calorically perfect gas is assumed. Okay, and so we have again, as you see, this is indeed an application of the normal shock wave, but also very real life applied application, both related to applied aerodynamics and also flight mechanics, flight measurement systems of the aircraft. And we have a certain P01 and P1 before the shock wave, and we have a certain P02 after the shock wave, which is sensed by this front opening, and we have a certain static pressure after the shock wave, which are basically sensed by the side holes on the pitot tube. So basically, our problem is to analyze this case using whatever we learned so far, and then try to come up with a relation directly relating m infinity to these two measured quantities P02 and P2 after the shock wave. So, I mean, the first thing, of course, this our starting point, I must say, is the relationship between P02 and P2, because these are directly measured. These are directly measured. And the first thing that we use them for is to come up with the Mach number after the shock wave, so M2 value. So for relating 0,2 to 2, we use the isentropic relation, because if you remember our normal shock wave discussions, we said before the shock wave and after the shock wave, we have isentropic flow, not across the shock wave. So we can relate P02 and P2 isentropically. So using the isentropic relation between 2 and 0,2, let's say, we can relate these two pressures, P02 and P2, which both of them are measured by the sensors inside the aircraft that are attached to the pitot-static tube, is equal to 1 plus gamma minus 1 over 2 m2 square to the power gamma over gamma minus 1. So therefore, using these two measured quantities on the left-hand side of this equation, I can actually obtain a value for m2 square behind the normal shock wave in front of the pitot-static tube. So this becomes, so I can get that, but what I additionally know, so in addition to this equation, what I also know, and then I will combine these two equations later, is that the Mach number after the shock wave, we have learned that is also related, it's also related to the Mach number before the shock wave. And in fact, if you know the M1 value, M2 can be calculated as well. So M1 square gamma M1 square minus gamma minus 1 over 2 is the value of M2 as a function of M1. So if we combine these two equations, now I end up with a relation that relates the two measured quantities, P02 and P2, to the inlet Mach number. So let me first write this down. So this is going to be equal to 1 plus gamma minus 1 over 2 m2 square. So m2 square, I have it from the second equation. So let me write that one here. 1 plus gamma minus 1 over 2 m1 square divided by gamma m1 square minus gamma minus 1 over 2 to the power gamma over gamma minus 1. So now the right-hand side of this equation, it's nice. It's only a function of the flight Mach number, basically. The Mach number in front of the shock wave. On the left-hand side, these are basically measured by your sensors inside the aircraft. So the thing is, of course, what I would like to know is N1. So basically, if I try to relate, if I then do some, mathematical exercise on this equation, basically what I can get, it's not a very straightforward equation, as you see, to get M1 to the left-hand side and isolate it and dump everything to the right-hand side. It requires some, few steps of mathematical manipulation. So first of all, P02 over P2 must be taken as an exponent gamma minus 1 over gamma to leave this as 1 plus let me check. So gamma minus 1 over 2 multiplied by this thing again. And okay, let me quickly okay, I will write I will skip one step to save some time, but okay, because you know what I'm trying to do here, and then it will look something like this. This is going to be equal to, after some rearrangement, I mean, you see what I'm talking about. You do the multiplications, rearrange the equations, simplify them a little bit, and then we get this term, for example, n1 square 2 gamma over gamma minus 1 plus gamma minus 1 over 2 divided by 2 gamma minus 1 and 1 square minus 1. And then from here, we get, I mean, you can do this yourselves, I guess. So you can just add these two terms. And now we do a simplification here. We call this term, I mean, to have a simpler looking equation, we call this term A. We call this term B, and we call this term C. And by the way, here B, after doing this addition, B looks like this: 4 gamma plus gamma minus 1 square divided by 2 times gamma minus 1. And then when you rearrange the equations, it looks something like this: A times C and 1 square minus A is equal to n1 square times B. And from here, A times C minus B times n1 square becomes equal to A. So therefore, if I would like to calculate n1 from here, it becomes equal to square root of term A divided by A times C minus B. Okay, and A is actually the pressure ratio, which is measured. So this is measured. C is just this term for a calorically perfect gas. You can plug in the gamma value and find that. Similarly for B, you can plug in the gamma value and find that, and plug everything into this equation. You get your flight Mach number. So if I open up these terms at the very end, and 1 is equal to basically now P02 over P2 to the power gamma minus 1 over gamma. So this is measured, it comes in from the sensors. And then A times C, so A is equal to P02 over P2 gamma minus 1 over gamma times 2 gamma, gamma minus 1 minus b, which is 4 gamma, gamma minus 1 squared, 2 over gamma minus 1. Okay, so this relation is therefore our final relation to, and by the way, I say M1, M1 is the Mach number right in front of the shock wave, just ahead of the pitot static tube at the nose of your aircraft, but the flight Mach number will be very close to that, okay? Very close to that. So since the flow is uniform ahead of the shock, a normal shock wave, so we can safely say that this is true. So ahead of the shock wave, this will be your flight Mach number. And all this equation is basically coded into the flight computer of the aircraft. So depending on what it measures from its pressure transducers connected to the stagnation pressure hull and the static pressure hull, it converts them to, it calculates this ratio basically. And then either assuming a gamma value, or if possible, it can also calculate, if possible, that aircraft can measure temperature somewhere. In the free stream, using the temperature, it can actually calculate CP and CV values and calculate the actual gamma value. Otherwise, just use the standard gamma value, and using this equation, which is coded into the flight computer, the aircraft knows its actual flight Mach number. Okay, so this is a little bit more involved than a subsonic aircraft, as you might guess. In a subsonic aircraft, there's no shock wave, first of all, in front of the pitot tube. So therefore, what we are getting and what we are basically using is directly Bernoulli equation-based calculation, which relates the stagnation or total pressure to static pressure, and we use that directly to drive velocity, in fact, velocity, okay? This is for measuring Mach number, and especially when you're flying with a supersonic aircraft, okay? So this was kind of an example application or of to show you the importance of normal shock waves in supersonic aircraft design. One little example. Good. So now I will go back to my other whiteboard, and we started talking about oblique shock waves. At the very last second, actually, I was giving an example, but I realized that I was already disconnected. I'm just checking if I'm connected now. And looks like I am connected. Duyuyorsunuz. Okay. So I was apparently talking to myself for the last 5 minutes last Thursday. Then I realized that I was already cut off. Anyway, so let's go back to our topic now. So oblique shocks, we have actually discussed most of it. In the last second, I was discussing an important thing, in terms of application, and the pictures that you are seeing here is related to that. The application, I mean, the first application we talked about is if we have some kind of sharp nose that creates an oblique shock wave. The geometry angle was theta, the shock wave angle was beta, and we discussed shock wave properties. And I said this oblique shock waves also occur if we have a ramp in the flow field. So if we have a geometry like that, and on top of this geometry we have some supersonic stream incoming, this ramp, which is here, this is the ramp, creates an oblique shock wave like that. And these kinds of ramps are frequently used in aircraft intake design, supersonic aircraft intake design. One example I'm giving here is from using the F-15 fighter aircraft. I would like to show a few things. The thing is, the the intake is shown here, and you know that in the fuselage somewhere at the back you have actually the engine. Now the engines cannot operate when they are subjected to supersonic airstream, so the airflow must be decelerated to subsonic speeds right in front of the engine, and we do that task using a supersonic inlet design. You will learn this probably in propulsion too, but there are certain things that are overlapping with aerodynamics class, because this reduction in Mach number, let's say this aircraft is flying at Mach 2, but the right in front of the engine, the compressor of the engine requires a Mach number around 0.4, 0.5. So this reduction in Mach number must be done through the inlet, and we do that reduction generally by a series of ramps like this. Okay, so what we do is the aircraft receives some kind of, if it's flying supersonically, this is a supersonic speed, then the intake is designed such that this is, let's say, the outer edge of the inlet. First, we generate a series of oblique shock waves. Let's say in the first ramp, this is an oblique shock wave generated here. Generally, generally we have a second ramp in this aircraft. A second ramp, this generates a second oblique shock wave in the design condition they call as here. And then once the Mach number is sufficiently reduced, we generate, the geometry is designed such that we end up with a weak normal shock wave. And then once the flow is subsonic, so the streamlines go like that. And once the flow is subsonic after the normal shock wave, we increase the area to decelerate even further. So we end up, our engine is somewhere here. So this is one example. So designing intakes, supersonic intakes like this, therefore requires a very good knowledge of oblique shock waves. And this is one important example. And the specific example that I'm using is the F-15 inlet. F-15 inlet has two compression ramps. So one here, which sits at 7 degrees here, you see that. And another one here, actually three ramps, 7 to 26 degrees. And then probably somewhere here, it generates a normal shock wave and then decelerates subsonically. So all these ramps in these types of aircraft are mechanically actuated, so their angles can change. Not only the ramp angles, so in our case, in our oblique shock wave relations, we are talking about this angle. This is generally variable. And if this is variable, it's called basically a variable geometry inlet. And then, so the aircraft can operate at in a wide range of supersonic speeds. The top part is also movable at F-15 design, so that at high angles of attack, so for example here, this dashed line is for low angle of attack operation when the aircraft is operating at low alpha, but at high alpha, it tilts this inlet towards here to operate at high angles of attack and catch the mass flow rate of air that is needed by the engine. Anyway, so you can see some pictures here. One extra information for you is that you can see the inlet is here, but you can see the inlet actually is not basically attached to the aircraft. So there's actually a gap here. I don't know if you can see that. Okay, there's a gap here. That has a special purpose in any inlet design like this, even for other aircraft like F4, F104, those old style, or even for F-16 and F-22, I'm not sure. But this gap is important. This gap is to compensate for the boundary layer growth on the aircraft. We will see what boundary layer is in this class, but a boundary layer grows on the surface and it has a certain thickness when the flow reaches the inlet position. Then since boundary layer means low momentum fluid, we don't want to get that low momentum, low kinetic energy fluid, we want that to live outside the inlet. We don't want to feed that into the engine, so we separate the intake a little bit out. This is more or less the boundary layer thickness here. Okay. Anyway, we will talk more about it in the topic of the boundary layers. But in the context of oblique shock waves, this is quite, this is one very, let's say, direct application of oblique shock wave knowledge that we will learn in this class. So when this, so whether it's a ramp type flow like that, or whether it's basically wedge type of flow that we talked about last week, those kinds of flows generate oblique shock waves. Now, another type of another flow physics, I must say, I shouldn't have said type, but another, well, I can say another type of flow physics that occurs in supersonic flow is what we call expansion waves. So, for example, if we have a geometry like that, so on top of which we have a supersonic airstream, and suddenly we have the geometry not actually doing the opposite. We have the opposite geometrical change compared to a ramp. If it was a ramp, it was basically going like that. But instead of doing that, if the geometry actually turns down, so it actually goes like this, okay? Moves down. So suddenly, I mean, basically what happens in reality is if we have, you know, somewhere out there far away from the surface, let's say we have an imaginary streamline, so it's something like that. What the flow in between this faraway streamline and this body suddenly experiences a sudden change in area. So the initial area between the streamline and this body was like that, but after this corner, suddenly it's a big expansion. The area suddenly increased. When this happens, and by the way, opposite is the case. It was the case for the ramp case. The area suddenly decreases. Actually, that's why we call it. We say, oh, the area is decreased. The gas is compressed. We say gas is compressed. So when gas is compressed, because of the sudden area decrease, it creates an oblique shock wave. But in this case, the area, the flow experiences a sudden increase in area. Then we say there is actually expansion happening. Expansion means that expansion happening, expansion of what? Expansion of this supersonic airstream, okay? So this kind of flow field, it does not generate what we call a shock wave. The thing is, this disturbance here happened almost instantaneously at this very sharp corner. And because of the sudden area change, of course, you might expect that the Mach number here, so again, if we call it M1, for example, the Mach number here, M2, will not be the same as M1, first of all. And in reality, we will derive their relations later. In reality, that this kind of sudden expansion causes an acceleration of the flow. M2 will be even larger than M1, okay? And opposite to what's happening in an oblique shock wave, M2 was getting reduced. It was deceleration because it's basically compression. But here we have the physical process of expansion. In this expansion, generally, I mean, when we have expansion, we do not have shock waves. But of course, the thing is, this kind of sudden change in geometry, this information must be propagated through the gas stream so it can adjust itself to M2 conditions. This happens through what we call an expansion fan. So again, we see lots of waves in the flow. So these dashed lines could be many waves, one after another. As the flow slowly goes through each and every single one of these waves, it actually gets accelerated and changes direction. This type of flow pattern in compressible aerodynamics is called an expansion fan. Expansion fan. So it's basically many number of very weak, let's say, Mach waves, or let's say isentropic disturbance waves, expansion fan. So these waves, as the airflow, supersonic airstream keeps hitting one after another, these individually very weak, but in total, it has a strong impact. The flow changes direction and adjusts itself to this geometry now, here the changed geometry, and then because of the area increase, it also experiences an increase in Mach number. So these two concepts, meaning occurring in supersonic flows, and the oblique shock waves and expansion fans are our next topic now. That's our main topic in this part of the semester. So just to remind you, and what we are going to do is basically we will first focus on oblique shock waves, then we will come to expansion waves. Sometimes we call it expansion waves as well. We will come to expansion waves. We will, similar to what we did when we were working on normal shock waves, we will derive equations. We will find relations that are relating, before the shock, after the shock, or before the expansion fan, after the expansion fan. We will obtain those relations. But before that, there are certain, there's another fundamental concept that we would need to learn at this stage. We have actually talked about it a lot at this stage, but now we will learn a little bit more about it before we start deriving equations for oblique shock waves. If you remember, I think we have also watched videos about this. The thing is, in any flow field, so even in subsonic flows, okay, that is, in any flow field, if there is some kind of object, solid object, this could be this little cylinder here, or it could be your aircraft, whatever, is subjected to this airstream, okay? Or vice versa, you can imagine the other way around. The object could be object actually can be moving at a certain Mach number, right? So basically, any disturbance that is created inside this airstream is propagated around. So it's like waves, like we have talked about. So in a subsonic flow field, that's a low subsonic flow, the fact that this object actually exists here gets propagated, this information gets propagated out with speed of sound of this medium. If it's air, it gets propagated outwards with the speed of sound, whatever that speed of sound is at that temperature, for example, in all directions. Okay, so each of these circles could represent, one wave propagating out from the solid object. So these waves that are propagating out at speed of sound basically carries one information. They carry the information that the object is here. Okay, the object is here. So when a fluid particle is approaching or is coming towards this object, let's say we have some kind of fluid particle, coming in at infinity, which is, let's say, low subsonic, coming in towards this object. The thing is, even before this fluid particle actually reaches the object itself, it first sees these waves that are coming out from this particle, and these waves will tell this fluid particle that, hey, look, there's a solid object down there. So just be careful, just be aware that you will encounter a solid object. So this information is propagated to this fluid particle. So therefore, fluid particle has quite a bit amount of time before it actually reaches the solid object. So what happens is in subsonic flow, for example, when you draw a streamline, you see that streamlines will start to, let's say initially they are perfectly horizontal, they will start to deviate from being horizontal such that fluid particles will adjust themselves even before they reach the solid object, and they will adjust themselves so that they will move around the object. Okay, so because they have ample amount of time and they know that a solid object is here, so they are adjusting their trajectory. And that adjustment is due to this propagation of waves. The information has already reached the fluid particles. Now, when the flow is supersonic, or the object is moving supersonically, now it's a quite different story, because what happens is now, if we have the same object, and let's say now moving to the left with some supersonic speed, again, it will keep emanating waves that the same waves that we were talking about here, it will be emanating waves, but the wave it will be propagating with speed of sound. So it will start diffusing around with speed of sound, but the object is moving faster than the speed of sound. So it will basically start leaving these waves behind, okay? So all the waves that it actually generates, it is moving faster than any of them. So it will keep these waves actually behind, okay? So these disturbance waves that are propagating with speed of sound will form what we call a Mach cone around this body. So all these boundaries of waves, so this is boundary of this wave, this is the boundary of this wave. Of course, you can imagine we have, probably millions of waves here. For example, the boundaries of these waves will coalesce together to form a boundary like that, okay? To form a boundary like that. This is known as a Mach cone. Mach cone. It's basically the envelope of disturbances. So all the disturbances that are created, the waves, are within this Mach cone. Everything is here. Outside the Mach cone, there are no disturbance waves whatsoever. Well, this is bad news for a fluid particle, because the fluid particle, let's say it's standing here, as the object is moving towards it, it has no idea. I mean, it will not receive any information, because the waves cannot propagate upstream of this object. So it has no idea that a very fast moving object is coming towards it. So basically, as the object moves towards this fluid particle, almost instantaneously, at that very instant, it realizes that a solid object. So it almost instantaneously has to adjust its position. So generally, that's what happens when we have a shock wave, an oblique shock wave, for example. So streamline is coming like that, and it has no idea that this object is here, and suddenly, almost at this instant, through this oblique shock wave, it has to adjust its direction. So this Mach cone, which includes all the disturbances downstream of this supersonically moving body, its angle can be calculated. So if let's use a different color here. Let's say this is the center line of this flying body. Yeah. So of course, the Mach cone angle, we call it, okay, or sometimes it's also said on the Mach angle. This angle is defined as the Greek letter mu, okay, mu. And you can see that it can be calculated. How? For example, when I mean, the object, first of all, is moving, let's say, with a velocity v. And this velocity, we know that it's greater than the speed of sound because it's flying supersonically. So in a time amount of t, let's say a t amount of time, so many seconds, so many hours, the object will move v times t amount to the left. And in the same time interval. So let's say it moved so many meters in this time interval, the object moved to the left. The propagating waves will have moved, basically will have moved out, and they are moving with speed of sound, which is slower than v. They will diffuse around with, let's say, amount of a times t. So because they are moving out with speed of sound. So in a certain time instant, the body has moved v times t amount to forward from this position to here, for example. In the same time, the waves only moved from this position to here with the amount of a times t. So now you can see that this angle here is actually, and the waves are, this is 90 degrees. So you can see that this angle is actually, can be calculated with, if you know the v and a. So from this geometry, the Mach angle sine mu is actually equal to a times t divided by v times t, okay, in the same amount. So from this triangle here. And so t's cancel out. So this becomes equal to a times v, which is basically 1 over the Mach number of the object. Okay, so the angle itself, the Mach angle, is actually equal to sine, inverse sine of 1 over m. So which means that in supersonic flow, that is, in subsonic flow, we do not have this phenomenon in supersonic flow. So this Mach angle, which contains the angle of disturbances, can be calculated if you know your flight Mach number. So depending on how fast you're flying, meaning how high your supersonic Mach number is, it could be a very strong Mach cone, or it could be a very weak Mach cone. But in any case, so this is basically, I mean, the concept of these disturbances and the fact that the object is moving and leaving behind all these disturbances, and these disturbances coming all together, which we call coalesce together in the boundaries and create this Mach cone, is the fundamental concept behind oblique shock waves. Okay, so which is basically what we call a wave front. Okay, wave, this Mach cone is a wave front because it's like all the waves coalesce together to form this. So an oblique shock at the very nose of the aircraft, like if it's a wedge or if it's a ramp, is a result of this physical process. Okay, and so therefore, when we are actually analyzing, and if we have a strong enough Mach cone, so that the wave front is strong enough, it's not very weak, we end up with an oblique shock wave in the very front, let's say, of the aircraft. So it looks, let's say, something like that. And to be able to calculate this is very important. This shock wave angle will be sitting at a certain angle beta, and the angle of the shock wave will depend on two things: the geometry angle theta and the free stream Mach number, which will be a supersonic Mach number. So this whole physics that I just described is the main, let's say, reason that we encounter these shock waves that exist around the supersonic flying aircraft. And if I remember correctly, I think maybe in the first class we watched some supersonic flying fighter aircraft. We watched some videos, and I have shown you those actually oblique shock waves that are forming around the aircraft, and also the Mach cone, if you remember. If you may want to, if you want to see that video, you can watch our class video again. I think it was the first week. Good. So what we are going to continue with is, so therefore oblique shock waves are extremely important for us to be able to actually design supersonic flying aircraft and other systems like supersonic flying aircraft, for example, the intakes and similar subsystems. So we will derive, similar to what we did for normal shock waves, we will derive relations for oblique shock waves now. That's what we're going to do in the next hour. So let's, it's 2:32. So let's give a break and then let's meet again at 2:40. So now first we will focus on how to analyze problems with oblique shock waves, okay? So similar to normal shock relations, we will try to understand, actually we will see, actually we can make use of normal shock wave relations that we have learned so far. So in the analysis of oblique shock waves, so oblique shock relations. Okay. So basically, what we're talking about is we have a shock wave that is sitting at an angle to the free stream. So M1, let's say, is coming in like that. Okay, let me redraw it so I can reproduce the sketch in my note. So M1 is, let's say, coming in like that. It is supersonic. And then the velocity after the shock wave, it will be tilted so that it can actually adjust its direction to the geometry. So basically the Mach number vector or the velocity vector, basically, let's say V2 here, must be sitting at an angle theta, and this theta is basically could be the angle of your, for example, ramp or the wedge, whatever, which one you have. So this is the angle of the solid object. So the flow, if the flow has to, it has to follow the surface geometry, right? So I mean, under nominal conditions at least. So if it's following the surface geometry, this means that it has to be parallel to the surface and sitting at an angle theta. Now, the shock wave angle, on the other hand, is not equal to theta. Shock wave is sitting at a different angle. And this angle is, as we defined it before, it's beta. Okay. So the incoming flow is supersonic. It is, the Mach number is basically related to a velocity here before the shock wave, and the velocity vector here actually, and the velocity vector after the shock wave adjusted itself so that it's parallel to the surface. Now the thing is, since the shock wave here is sitting at an angle to the flow, basically the first thing that we do generally is to decompose the vectors, relevant velocity vectors, into their two components. One component that is actually normal to the shock wave, this one, so this sits at 90 degrees to the shock wave, and another component that is actually tangent to the shock wave. Okay, so let's call them V normal 1 and V tangent 1. So after the shock wave, we have V2 that can also be decomposed into two components. Basically, this one, which is normal to the shock wave, V and 2, let's say, and another tangential component, which is tangent to the shock wave, VT2. Okay. So the thing is, if you remember what we did when we were discussing normal shock, when we were trying to obtain normal shock wave relations, is that we actually selected a control volume and actually applied conservation equations into that control volume, using that control volume, and obtained at the end the what we call normal shock wave relations. We do similar thing here. We take, for example, if we take a control volume normal, or in a box that includes in a box which has walls that are, let's say, or surfaces, not walls, but surfaces parallel to the oblique shock wave, it looks something like that. Now the thing is, the main momentum change. So, for example, along the surface, it will be equal to P1. Along the surface, it will be equal to P2. But half of the surface, it will be P1 here and P2 here, and P1 here and P2 here on the side surfaces. Now, if you write down the, first of all, for example, mass conservation, continuity equation, okay? Continuity equation says that whatever mass is incoming, it should go out, right? So we have certain mass incoming from these surfaces, this surface, and same mass has to go out from this surface, and we have in the normal direction, that is. And similarly, we have some mass incoming in the tangential direction. It has to exit also from here. In reality, if you do the mass balance, basically we see that in an oblique shock wave, the mass flow rate balance is basically it's basically needs to be conserved, and it's driven by the normal normal velocity component. The reason is that in the normal direction, the flow actually experiences the shock wave. It does not experience it in the tangential direction because the velocity is basically parallel to tangential direction. It just flows parallel to the shock wave. However, in the normal direction, it crosses the shock wave. Actually, in the normal direction, the flow sees as if there is a normal shock wave, not an oblique, but a normal shock wave standing right in front of it. So basically, our discussions, or everything that we did for the normal shock wave analysis, is valid here exactly for the normal component of the velocity. In a normal direction, it behaves like a normal shock wave. So whatever continuity we have in the normal direction, Vn1, in terms of mass conservation, for example, it should be written in this manner. Now, regarding momentum conservation, as I said, the main momentum change, what is momentum change? For example, when the flow crosses or moves across a shock wave, it feels sudden deceleration, reduction in velocity, so sudden reduction in momentum. That sudden reduction momentum, of course, occurs mainly in the normal direction as well, because whatever normal velocity component we have here, it will feel that deceleration because it will act, the oblique shock wave will act such that to decelerate, to reduce the momentum of the flow in the normal direction. So we can use, if we use the same equation here, P1 rho 1 u v n1 square, so normal velocity, so that momentum balance should be satisfied in the normal direction as well. In the tangential direction, the thing is, since everything is happening basically parallel to the shock wave, okay, basically parallel to the shock wave, and the pressure forces are all balanced out. Anyway, I mean, if you look at here, this is on this surface, we have P1, parallel to the shock wave, we have P2, pressure forces are all balanced out. And in the tangential direction, there's nothing that can change, for example, the momentum of the tangential component of VT1. There's no shock wave, there's nothing. So basically, the momentum of the flow in the tangential direction is kept constant. It does not change. That gets reflected to the momentum conservation equation, is that the tangential velocity component does not change across the shock wave. So V tangential 1 must be equal to V tangential 2. So we have two conditions to satisfy conservation of momentum across an oblique shock wave. The first condition is that the normal component must satisfy this equation. And the second condition is that the tangential component must not change. Tangential component of velocity, everyone. So generally students get confused. Tangential component of velocity is kept constant, but tangential component of Mach number will not be a constant. Okay, this is not true. Any ideas why this is not true?
Rho is changing, sir.
What is the relation with rho and Mach number?
The speed of sound change, I mean.
Speed of sound changes, yes. Why does the speed of sound change? Because the temperature changes. Static temperature, that is. Static temperature is different in any case across the shock wave, whether it's oblique or normal. How much does it change? It depends. In the case of an oblique shock problem, it depends again on the normal component of the oblique shock, how much the static temperature changes. We will see that equation. But anyway, the tangential component, so since the speed of sound will be different, tangential component of the Mach number will not be the same. But the tangential component of velocity will be the same. Okay, it will be the same. The major change will occur in the normal component of velocity, and therefore the normal component of Mach number as well. So these two things were regarding continuity and momentum, so mass and momentum conservation. Now regarding energy conservation equation, we have our state of the gas before the oblique shock wave, and still this is valid, meaning the stagnation enthalpy or stagnation temperature does not change also across an oblique shock wave, because it is at the end of the day a shock wave, and it is an adiabatic process, right? So stagnation temperature as enthalpy and temperature are kept constant. So this is actually H01, and this is actually H02. So this is kept constant, but we know that what is V1 square, for example, that's the magnitude of the velocity vector. So it includes both the tangential and the normal component. So the magnitude of it is actually equal to V normal 1 square plus V tangential 1 square over 2, and H2 plus V normal 2 plus V tangential 2 square over 2. Of course, since tangential velocities, they do not change, this also translates into the fact that normal component of the total enthalpy also must obey this equation, H2 plus Vn2 square over 2. So this must be satisfied in terms of conservation of energy. So so therefore, as a result, what I can say is this: for an oblique shock, basically what we do as a summary is to use normal shock relations for the normal velocity component, or for the flow, to make it more precise, for the flow that is in the normal direction to the oblique shock, we just use normal shock wave relations. That's it. And for the tangential component, we know that the tangential velocity is not going to change. So remembering the normal shock wave relations, for which we derived previously, we basically use exactly the same equations, but now only for the normal component of the shock wave. For example, the normal component of Mach number after the shock wave can be calculated as a function of the normal component of the Mach number before the shock wave. Okay, so this is how we handle normal shocks. Oblique shock waves. Similarly, for example, the density change across a normal shock wave, oblique shock wave, is again calculated by using the normal component of the incoming Mach number. So 2 plus gamma minus 1 times mn1 square, and also the pressure rise across an oblique shock wave is also calculated as a function of the incoming normal Mach number. And regarding temperature, once you know density and pressure ratios, you can calculate it yourselves. This is P2 over P1 times ρ1 over ρ2. Just multiply these two equations. So as you understand here, finding, what is normal? What is normal Mach number? Mach number, normal component of Mach number before the shock wave. As you might very well guess, it completely depends on the geometry. So we need to calculate the Mach number corresponding to this velocity, okay? And this Mach number must be related geometrically to the object that is actually generating this oblique shock wave. So what I'm trying to say is it must be related to this theta angle, okay? So in fact, just by using the trigonometric relations here that exists in this geometry, you can write an expression for example, for the normal Mach number, mn2. This is basically m2 times sine beta minus theta from this geometry. I will scroll up again for a second. Okay, so basically what I'm trying to say is this is m2. Okay, its normal component is this. So this angle here is basically beta minus theta, right? You can see it, I guess, from the sketch here, beta minus theta. So the normal component mn2 is basically m2 times sine beta minus theta. So now when we start talking about theta, that's the shape, that's the angle of the nose of your aircraft or whatever, or the angle of the ramp in your air intake, whatever. So this is your flight vehicle, basically, theta. Now, if I take m2 to the left-hand side from here, so it becomes equal to the normal component of Mach number divided by this angle, sine beta minus theta. Okay. Now there are, of course, two unknowns here, okay, in this equation. I mean, let's take a look at this equation for a second. Mn2, in reality, we do have an equation for this. Mn2 is here. So this is that equation. If you know the normal Mach number, okay, Mn1, then Mn2 can be calculated. Theta generally is an input, so it's your geometry. What we do not know is these two things, M2 and beta, the shock wave angle. We don't know that, okay? So in order to find that, we need to dig a little bit more deeper. First of all, from the geometry, I can write, for example, a geometric relation between beta, tangent beta that is, tangent beta, and the velocity components un1 and u tangential 1. So I said v in my whiteboard here. So vn1 divided by v tangent 1 is actually equal to tangent beta. Again, sorry for this. I have to scroll up again. So you can see that this is beta, this is beta. So basically this is vn1. So vn1 tangent beta is basically vn1 divided by vt1. So this is beta. So you can see where that's coming from, right? So that's tangent beta. And also from the geometry, I know one more thing. I know tangent beta minus theta, which we defined this angle just a second ago, a minute ago. So this is actually equal to v normal 2 divided by v tangential 2, okay? So basically, from here, if I divide these two, so dividing tangent beta minus theta by tangent beta, so this becomes equal to Vn2 divided by Vt2 and divided by Vn1 divided by Vt1, okay? And of course, tangential velocities are equal, so they cancel out. This becomes equal to Vn2 over Vn1. And from continuity equation, this becomes equal to rho1 over rho2. Okay, rho1 over rho2 from conservation of mass equation. Now from here, the normal another thing that I know is that the normal component of Mach number at 1 is also related to beta from geometry. This is known. Now, if I combine all of these equations, I get a relation between the geometrical deflection angle theta, so that's our flight vehicle basically, whether it's its intake or its nose, the relation between theta angle, tangent theta, as a function of flight Mach number n1, or the free stream, let's say, to keep it generalized, free stream Mach number n1 and the shock wave angle beta, 2 times cotangent beta multiplied by m1 square sine square beta minus 1 and divided by m1 square gamma plus cosine 2 beta plus 2. So this equation is basically the most important equation that we use to calculate shock wave the properties of a flow across an oblique shock wave. This is called the theta beta m relation. Okay, theta beta m relation. So theta beta are those angles. This is the geometry angle, shock wave angle, and free stream Mach number. The thing is, the unknown here is, as you can see, I mean, what are the inputs? Generally, the inputs are, you know, my flight vehicle is an input, the geometry. I know it's probably a shape, or I'm trying to design its shape. I'm trying to determine theta, or for a given flight vehicle, let's say, I know theta. And if somebody says, okay, this aircraft is going to fly at this altitude and Mach number, so I know M1, the unknown here in this equation is beta, okay, the shock wave angle. So given a certain geometry and given a certain Mach number, flight Mach number or free stream Mach number, I need to use this equation to find the shock wave angle. Why is this important? Because if I know shock wave angle beta, I can put it into this equation and calculate the normal component of the incoming Mach number. And as soon as I know my incoming Mach number normal component, I can make use of all these equations up here to start calculating my normal Mn2, for example, after the shock wave, which I can use to calculate M2. And if I know Mn1, I can calculate the pressure ratio, static pressure ratio, density ratio, temperature ratio, and similarly stagnation pressure ratio and all that, okay? So therefore, a determination of the shock wave angle is of extreme importance, or the, let's say, first priority that we need to do in oblique shock wave analysis problems. And we use this relation for this, the theta beta m relation. And as you can see, it's not an explicit relation, meaning that it's very difficult to isolate beta to the left-hand side of this equation here, okay? It's not so easy. So for this purpose, we generally use what we call a theta beta m diagram or chart, theta beta m diagram, or plot or chart or whatever, okay? This theta beta m diagram actually helps us determine this beta value, shock wave angle, for a given flight Mach number condition and for a given deflection angle condition, theta. We will see, I will show you the diagram that is also in your book, but I will show you that diagram to actually calculate how we actually use it. But there are certain aspects of this equation before I go there, before we start talking about how we use that chart to be able to calculate the shock wave angle for a given flight Mach number and geometry condition. There are certain things that we observe about this relation. Let's say some important aspects. Okay. Now, for the first aspect is that for a given Mach number, so for a given Mach number M1, okay, so somebody says, okay, I have this geometry and it's going to fly at Mach 2, okay, for a given Mach number. The thing is, this equation shows that there is a maximum value for theta. So there is a maximum, let's say, max possible deflection angle. So we can call it theta max, okay? which means that for this relation to hold, this equation to hold, and if you put if you insert here m1 as an input, corresponding to this m1, there's in reality a maximum value for theta that can work, meaning which means that this equation will be true for theta values below that theta max value. Equation will not be valid if the theta value is above that. So it will not produce any solution for beta, basically. That's mathematically what I'm trying to say. It will not produce any beta if that theta is over theta max. By the way, theta is an input, don't forget. We are not only inputting this M1 here, this is an input, this is your flight condition, this is also an input, this is your geometry. So the thing is, this equation tells us that these two must be consistent with each other, meaning that you cannot just put any Mach number and expect this equation to work. No, you cannot do that. For an M1 value, there is a maximum value for theta max, and this equation will hold only if this theta on the left-hand side of this equation will be less than that maximum value. If you somehow input a value that is larger than theta max, this equation will not be satisfied. It will not be equal. The left-hand side will not be equal to the right-hand side. Then physically, what happens in that case? And what does that mean physically? So are we not going to have an oblique shock wave because we cannot have a solution for beta? Physically, what happens is, if that is the case, if for some reason you selected when you're designing your aircraft, by the way, don't forget, I'm saying it again, theta is an input. Okay, you are selecting it, for example, as a designer in your aircraft designer, a missile designer, intake designer, whatever, you are choosing this theta. So if you somehow, let's say, was not careful enough, you selected this larger than the theta max that is allowable for your flight Mach number, then it will not produce in any beta. And physically what it means is we will not, so no attached oblique shock will observed, no attached oblique shock. Instead, we will have what we call a detached shock wave. Instead, a detached shock wave will be observed. Okay, and if it's a detached shock wave, it's not an oblique shock wave, so all the relations are basically not satisfied. We cannot use theta beta M diagram, and we will see that condition visually when I show you the theta beta M diagram. So this is one case, just there's a little sketch here. Let me try to replicate it. So if we are talking about like a simple wedge with a certain angle here, theta. Now, if this theta is less than the allowable theta max for a given Mach number, supersonic incoming Mach number condition, we will have an expected oblique shock wave here. But if we have if we are flying at the same Mach number, but somehow we selected a larger, we have a solid body, let's say, with a larger theta, and this theta is so large that it is larger than the allowable theta max value, there will not be any oblique shock wave attached to this nose here. This will produce what we call a detached shock wave like that. Okay, so for theta greater than theta max, this is what happens. Nature establishes a detached, basically a bow shock in front of it, which is something that is not desired when you are designing, because this kind of detached shock wave more or less acts like a normal shock wave here, which creates a lot of stagnation pressure loss compared to this case. This case creates very little stagnation pressure loss. Okay, so generally when we are designing vehicles, you need to be careful about this condition, whether your selection of I mean, you cannot just start drawing aircraft nose shapes as you want. So you have to be very specific to satisfy this condition. And mathematically, this equation also implies one thing: as flight Mach number increases, you know, let's say goes to infinity, to mathematically, which physically means goes to larger and larger values, theta max actually converges to about 45.5 degrees for air, okay, for air. So for every special or every specific inflow Mach number, there's a certain theta max value. We will see that condition on the chart, on the theta beta m diagram. The second aspect that is actually observed from this equation, the second aspect is that, let's say we are in the safe zone, we have a theta value that is smaller than theta max, okay? Now, for this condition, we know that this equation is going to be satisfied. So if you plug in your theta value, which is smaller than theta max, and if you plug in the corresponding Mach number value, the left-hand side will be equal to right-hand side. So this equation will be satisfied. However, this equation, I mean, you know, the unknown is for beta. Beta is the unknown here. It will produce, I mean, this equation will be satisfied in reality for two different beta conditions. I mean, two different beta numerical values will satisfy the same equation, okay? So for the same Mach number and same theta input values, you will obtain two solutions for beta. So let me quickly write this down. There are two oblique shock solutions for a given upstream Mach number, two oblique shock wave solutions for a given M1, let's say, for a given M1. Now this, we will also see that when we are discussing the theta beta M diagram, and generally one of them, one solution that is called a weak shock solution, and the other is called a strong shock solution, which means that from this equation, the result that we get for the weak shock solution has a relatively low beta value, numerically low number for beta. A strong shock solution generally has a numerically high value for beta, okay? And in general, in normal applications, wind tunnel tests and calculations, most of the time we observe in nature that a weak shock solution actually exists physically. We generally observe if you mathematically solve it and end up with two beta values, we generally observe the weak shock solution in our flow domains. So we are a little bit running out of time. I will continue this tomorrow, but before we finish today, I would like to quickly show you, at least, of course, we will discuss it in more detail tomorrow, but quickly show you how this theta beta M diagram looks like. Let me quickly share this with you. I think exactly the same picture also exists in your book. Let me save this as another file. Just give me a second here. Yeah. Olmadı, bir saniye. Evet. Okay, let me share this one. So this is what we call, what I've been calling the theta beta m diagram, or theta beta m chart. Just some very quick information here. The lines that you see here are the solutions of that equation, that theta beta m relation. On the x-axis, we have the theta angle, deflection angle. The y-axis is the beta angle, the shock wave angle. And you see that this chart is composed of many solid black curves. So one after another, they are drawn like that. Now, each solid black curve here, for example, I'm trying to follow one of them here, is for a constant m1 value. So for a given m1, so if you say your flight Mach number is 1.8, you probably have a 1.8, a curve along which Mach number 1 will be a constant, and that is going to be equal to 1.8. As the Mach number increases, so as you go to higher and higher supersonic speeds, you go towards right in this chart, okay? So let's say if this is for Mach 2, next one could be for Mach 2.2, next one could be for Mach 2.4, it goes like that. So from left to right, Mach number increases. So each black curve is a solution of that equation for a given flight Mach number. If you focus on for a second one of the curves, so this one, you see that as theta increases, beta for a given free stream Mach number, that is constant along this curve. So you are flying at the same Mach number, you are changing your ramp angle, for example. As you keep increasing your ramp angle, your theta, for example, shock wave angle also increases to higher and higher and higher and higher angles. And at some point, at this theta value, for example, which is a little bit over 25 degrees in the sketch, in this chart, maybe 26 to 27 degrees, the curve starts turning back, okay? So for this given Mach number, if your theta angle becomes higher than 26 degrees, there is no curve, basically. The curve turns back, and to the right of this curve, there's no solution for that Mach number. So this means that this is the actual theta max value for this Mach number. So when you are designing your aircraft, if this is your flight design Mach number, you have to be careful, you better be careful to choose your theta angle below that value. Again, coming to, tying this up to our second point that we just discussed, if you are below this theta max value, you are somewhere moving along this curve for a given Mach number, which means that for a given theta angle, let's say 15 degrees, this 15-degree constant line cuts this curve at two places, one here, and if you go up, one somewhere here. So for the same theta angle, we have two solutions for beta. One, a lower beta angle somewhere here in this range, and a higher beta angle somewhere here in this range. So the solution here at higher beta angles is called a strong shock solution, and the one down here is called a weak shock solution. And the line that is dividing actually is this red line, which basically passes through here, as you can see, almost following the theta max locations, is the strong shock, weak shock dividing curve. And generally, as I just mentioned, in wind tunnel tests and in nature observations, we generally see that the shock waves that we generate or that are generated, we experience, are more in this range, in the weak shock domain. Okay, and one, okay, there are many things that we will discuss about this, but I guess we are running. I cannot go into any more details in the last second. But anyway, we will pick it up from this point. We will discuss the theta, beta, and diagram more, and continue discussing the oblique shock waves and how we use this diagram in the analysis of oblique shock wave properties. Okay, any questions?
Hocam, when will we have our first laboratory work?
It will be, I mean, first of all, the laboratory work will be a video file. I mean, you will watch the video and some data will be sent to you. Assistants will coordinate it. I'm not sure right now, but I think it's getting close.
Okay, thank you.
Hocam,
Any other questions? Evet.
can we say that an accelerating supersonic aircraft would have exposed on detached shock wave somewhere in the accelerating point?
Yes, you can say that. It could be. Unless it has a variable geometry. I mean, generally, the nose will not be variable, but as I shown you in the very beginning of this class, for example, intakes are depends on the aircraft design, but in some aircraft has variable geometry intakes. So you adjust the ramp angle such that it will never be detached. But for the main shockwave in front of the aircraft, yes, you will experience at some points detached shock waves. But at least in the design condition, you don't want to have that. You want to have attached oblique shock waves.
Okay, sir, thanks.
Mm-hmm. Any other questions? Okay, everyone. So let's meet again tomorrow afternoon, 1:40, and let's continue. We will continue from this point. Okay. So let's stop recording.